Recording in progress.
Hey everyone, this is my Physics 12 or 2211 Lab 1. My name is Ansley Hightower. So the purpose of this experiment was to observe the position of an object with constant velocity using Newton's first and second laws. So some of the physics principles that we used in this experiment were obviously Newton's first and second laws, position and velocity update formulas, and then experimental model versus computational model. And the main lab result was the experimental and computational model of a tennis ball's position were similar, but had some variation due to experimental error. So some of the physics principles we used were Newton's first law: objects in motion will remain in motion, objects at rest will remain at rest unless acted on by an outside force. Newton's second law: force equals mass times acceleration, position update formula, and velocity update formula. The system in this experiment was the tennis ball, while the surroundings was everything else. The initial conditions, the time started at 0 seconds, that's position, and then the velocity in the x direction, which is most important, was 0.961 meters per second. So in the experiment, I rolled a tennis ball across the table and then put it in the tracker program. I only used the middle section of the video, so after I rolled the ball and then before it rolled off the table, and the tracker was calibrated using the tennis ball's diameter of 0.0661 meters, and the tracker's axis was tilted to align with the angle of the camera. So in the computational model, I had to change the mass, which is the system mass, to match the tennis ball, and then I put in the initial position and velocity vectors, which I just showed you. And then this while loop, it was to look at the position at certain time intervals, so every 0.1 second. And so the F net vector, which is zero net force, was 0 because there was no net force, there was no acceleration. It was just a constant velocity. And then we used the position update update formula and velocity update formulas to represent the ball's motion in this scenario. And so on the right here, we have the position versus time graph. And you can see it's very linear. It has a linear progression. It has a flat slope or like a continuous slope, so that the velocity graph would be just a straight line, which means it has constant velocity and 0 acceleration. So this graph shows the experimental position versus the model position, and you can see the experimental position, which was my video, it's a little bit lower than the model position that was gained through Python. And some potential error that could have caused this was from friction that was unaccounted for, movement of the ball from front to back, not just from left to right, and then the axis being tilted to match video framing. I could have made a mistake when I did that. If the positive and negative axes were switched, the lines of the graph would be sloping downwards instead of up and to the right. And is it possible to tell how many pushes and pulls were added together to give 0 net force? I would assume that the roll force and potential friction force are equal to 0 because I did roll the ball. So I gave it an initial force, but after it started rolling, there was no net force on it. So maybe that initial moment, there was a friction and that rolling force, but it's hard to tell without doing more calculations and trying to calculate a frictional force. So I don't know if it's possible to give a definitive answer besides that. So in conclusion, a net force of 0 newtons explains the constant velocity of an object. And this goes back to the velocity update formula. There's no net force, so that cancels out the mass and the change in time. So the initial velocity just equals the final velocity. And so the only thing changing is the position as time goes on. And then differences between the computational model and the experimental model can be attributed to human error using tracker, so like the tilting of the axis to match the ball could have caused an issue, as well as just frictional force outside of the tracker that we didn't take into consideration could have changed the experimental model so that it was different from the computational model. But that is it. Thank you for listening.